So let me introduce Colin to everyone here. So I know Colin for about 2 years now, I think something like that. He has a degree in science from University of Cambridge. You please correct me, okay? And he has a PhD in geophysics from University of Leeds. That's also in England, right?
Mm-hmm.
And he has an extensive research career being postdoc, holding postdoc positions at Oxford, Rennes, Columbia, and you spent a lot of time in Columbia, right? More than a decade.
Almost
And
20
Colin
years.
is now in Japan, in Blue Maple Soft. That's correct, right?
Yeah.
So just a little bit more details. According to the ResearchGate, he has more than 7,000 citations and I think more than 100 papers. Okay, I think his research is very, very interesting because it's a very nice application of classical physics to geomorphology. Say, I believe you great research goal was to understand the physics of geomorphology. So, and this is a very attractive field right now because you have a lot of satellites measuring and collecting data, and you are someone who have a real interest in all this data analysis technologies and content. So it's a very nice field to hear right now. So we got another mathematical physics, my colleague, Paul Eduardo, is now here. And welcome, you are very welcome, and it's a pleasure to hear you. We hope that once this COVID thing ends, you can visit us here in person.
Oh, that would be cool. Yeah. Okay. Thank you, Petrus. That's a kind introduction. Hello, everybody. Yeah. So I'm a geomorphologist, geophysicist, and tonight I'd like to present to you some theoretical work I've been doing. The title of the talk is The Geometric Mechanics of Erosion, which Petrus particularly likes, I think. The topic is basically the idea of introducing techniques of differential geometry and classical mechanics and geometric optics to understanding how landscapes evolve, and principally to understand why is it that landscapes achieve the geometry they do, the ubiquitous geometry that we see pretty much everywhere. So the structure of my talk's roughly along these lines. I'm first going to expand a bit on the why and the how of this idea, and show you some examples of modeling work that's already been done in the field. And then I'm going to pose a question and set a hypothesis for how we might tackle this geometry question. Then I'm going to introduce some ingredients, these ingredients of differential geometry and classical mechanics, it's mathematical and physics ingredients, and how we're going to put them together to solve for and find a geomorphic Hamiltonian, a Hamiltonian that expresses an essential aspect of how erosion proceeds in a landscape. And I'll show how we can solve that by, for example, ray tracing. I'll show how we can exploit the Hamiltonian to get, for example, Lagrangian. And for the mathematicians in the audience, slightly dangerous for me to be doing, but I'll show how I think this says that, reveals that the erosion process acts on a Finsler geometry of a sort, which brings some interesting aspects of the problem to light and also poses some problems. And then I'll sum up with a couple of suggestions of where we might go, where I might take this in the near future. So as a geomorphologist, I'm fundamentally interested in how landscapes evolve. And we're going to focus on uplands, mountains, hills, areas of net erosion, and not the lowlands with net deposition. In fact, we're not going to talk about deposition at all. We're talking about landscape surfaces of the Earth that take tens of thousands to many millions of years to evolve. So think of processes that act on that time scale. In reality, geomorphology is a pretty dirty business. It's very complex. It involves very complex interactions between tectonics, the mass input to the problem, and the influences of climate and local weather, the growth of vegetation, the weathering of the surface, physical and chemical erosion processes, the transport of material and the motion of water and ice over that surface, and the action of the moving water and sediment to induce erosion. But despite all that complexity and all those interactions, and their true feedbacks among all those processes in real landscapes, we can nevertheless boil things down and say that the essential physics of how a mountain evolves is driven by rivers. The rivers, you can think of the river network as like a skeleton, the erosional backbone of the landscape. And flood flow over that backbone along the rivers moves the sediment and abrades the bedrock and drives overall the evolution of that landscape. The hill slopes, where most of the sediment actually comes from, are subordinate to what the rivers are doing. So the channels erode, they drive landsliding, they suck sediment off the hill slopes and out of the landscape, and they carry it away. So if we focus on the rivers, we have the essence of how the whole landscape evolves. So in the field of geomorphology, at this point, we have pretty sophisticated models for example, how channels initiate, how they branch and organize into networks, the branching dendritic, typically dendritic networks, and the consequent development, evolution of the whole landscape. And there are some pretty sophisticated models and understanding. There's a lot of numerical modeling in this field. Feedbacks between climate and tectonics and erosion. In all the models, the numerical models, what we might call landscape evolution models, the geomorphologists have developed, I think it's fair to say that all of them essentially assume that it's totally okay to treat the landscape as a vertical field, an elevation field H that's a function of position XY, horizontal position XY, and time. In that sense, erosion is forced to act vertically down. It's modeled only as a purely vertical process. And lateral erosion, it's not so much ignored so much as it's implicit. The only way you can model a lateral erosion process, say trivially, the bank of a river involves lateral erosion, but it can't be modeled in these numerical models, except as saying, well, we have a rate of erosion on a slope, so there's an implicit motion sideways. Similarly, if you have a glacier flowing down a valley, the walls, you can't make a U-shaped valley without essentially having lateral erosion, but it can't really be modeled using the typical approach. And of course, if you have very steep topography, singular behavior in the gradient, you start to have problems too. So I, for example, wrote up one of these models a long time ago. In this picture here, you see a sort of a block uplift landscape with a fault running along the boundary here, a normal fault as we call it, which is a velocity slip boundary condition for this whole domain, which is being vertically uplifted. Mass is being input, and water falls over the surface and evolves by propagating into the interior, a drainage network. It pulls material out. And one of the questions I always had was, how fast does it take for a change in boundary condition at the edge, say a single earthquake pushes all this landscape up and makes a little edge here, a little fault scarp. How long does it take for that little fault scarp, like a little waterfall, how long does it take for it to propagate into the interior? How long does it take for that information to reach the whole landscape? While knowing that essentially erosion is acting pretty much downwards. And so that's essentially one of the motivators for this project. Here's a more recent model that deals with propagation of a channel into the interior in a much more realistic way than my model from 20 years ago. Just an illustration. This is just a taster really of what the field does. And here's a landscape that's so insanely realistic that I think we could be forgiven for thinking it's an actual landscape. Again, the colors here indicate elevation. Brown is elevation, and green through brown. Ignore the colors of the rivers here. So numerical modeling, assuming a height field, a 2+1D treatment of the elevation surface has become very sophisticated. But I think it sort of skates over this issue of what is the direction of erosion really? It seems like almost a trivial question to ask. If you ask a typical geomorphologist, they probably say that erosion acts vertically downwards because gravity, right? I've actually had a paper where we were looking at lateral erosion processes in a glaciated environment, where a reviewer, a well-known, respected guy, said, well, doesn't erosion just act downwards? So that would be a common answer. One might also say that because water flood flow drives sediment along a channel and drives sediment, advex sediment downstream, makes it hop and bounce and slide and induces impacts that are very oblique to the surface, one could argue that perhaps erosion acts in some direction oblique to the surface. You could also say, well, the only answer that makes any sense is that the surface moves in its normal direction because mathematics. Or we could say, well, the process acting on that surface is extremely anisotropic, in which case perhaps it's not as simple as motion simply normal to the surface. If you think of an analogy here, the propagation of a light ray or the propagation of a seismic ray in a very anisotropic medium, the phase velocity and the group velocity are not collinear. So the more anisotropic the medium, the more they diverge. So that kind of idea. But these sort of questions haven't really been raised in the field, to my knowledge. And the tools of differential geometry, etc., have not been applied to address it. Of course, some might say it's not clear whether that's necessary, but we'll see. So we know this. Here's a statement of probably the obvious, that the rate of change of landscape topography is controlled by that topography. In other words, the rate of change of landscape geometry is controlled by its geometry, reducing everything to its essence. We can think of this as sort of geometric straitjacket, that the evolution of a landscape is geometrically is controlled by its geometry. What we can do with this is say, okay, let's pose this as a hypothesis that fundamentally geometry is the driver of landscape evolution. Unlike perhaps the emphasis of the field for recently and for many years, which is to focus on the processes of erosion and transport and tectonics, etc., and then to say that the geometry arises as a result of those processes, rather than emphasizing in this hypothesis that geometry is the main thing. So how do we address this question and the hypothesis? So I said that the typical approach is to treat elevation as a height field, 2+ one-dimensional treatment of what's essentially a 2D surface in a 3D space. Instead, here, what we do is treat landscape as a series of time slices, where we can construct an implicit function in 3D space and the volume are occupied by landscapes, and say that at any given, this implicit function says that it's the arrival time of the surface at a given position, subtracting the current time, is that implicit function. So the position R of points on the surface at a certain arrival time t minus the current time defines our implicit function. In other words, topographic surfaces will be the zero level sets of that implicit function, which means we can use level set theory to say how fast does that topographic surface evolve. And if we have the local velocity psi, the inner product of that with the gradient of the implicit function, which would be grad t, which would be the slowness vector, the normal slowness vector of the surface, that reduces to the surface normal erosion speed multiplied by the modulus of that gradient of the implicit function, i.e. the slowness function. But I'm going to show that perhaps it's a better way to treat this is to, instead of using the normal slowness vector, we should use a normal slowness covector. And I'm not the best person to explain covectors and differential one forms, but I'm going to explain it in a very pragmatic way and show how by writing the erosion, we're going to construct an erosion model and write it in terms of this normal slowness covector, which will show why it's a useful way to treat the problem. So here's probably the most, how should I put it, simplistic way to think about a covector. And I'm going to conflate covector with differential one form here for simplicity. This is probably the most simplistic explanation of a covector you'll ever see. So bear with me. What this picture is showing is a vertical slice through the landscape with these arrival time slices in gray. This is the topographic surface at initial time. And we have a scale of 0.5 millimeter. We're really zoomed in here. And erosion is proceeding normal to the surface and making that 60-degree tilted surface erode at a uniform rate normal to itself at a rate of 0.25 millimeter per year, which is actually quite fast for geomorphology. And so each of these gray lines here is a successive arrival time surface of the landscape. And this darker line here is 4 years later. So we can describe trivially, I suppose, this erosion process using an erosion velocity vector in red here, and say that it points in the surface normal direction and has a magnitude of 1/4 millimeter per year speed. And then we can say, okay, that's the erosion rate normal to the surface. So what if I take the vertical component of that erosion rate vector, and it would be cos 60, so it would be 1/8 of a millimeter per year. But if you're sitting here and watching, like watching paint dry, you watch the land surface slowly drop 1 year later, and you're 1/2 millimeter lower down. So that the local vertical rate of erosion is 1/2 millimeter per year. It's not 1/8 of a millimeter per year. So naive, really naive application of an erosion rate vector, surface normal vector, and taking its components doesn't give you the vertical and horizontal rates of erosion. I mean, obviously, it's a trivial operation here. We can construct this triangle and get the vertical rate of erosion, no problem. But if we treat this motion of the surface using a covector, it makes things simpler. So a covector, right, P, the tilde on top is to indicate a covector, bold for vector covector generically. If we take the covector, the normal slowness covector, P, this covector takes in a vector, n is the unit normal vector. A covector takes in a vector and spits out a scalar. And specifically what it does is it counts the number of times this surface that it's measuring, it's describing. It says, give me a direction and a length. So in this case, 1 in this surface normal direction, and count the number of times the arrival surface is punctured. And in this case, 4 times, 1 year each of them. So it says 4 years over 1 millimeter, 4 years per millimeter. If you're a runner, think of this as a pace, a snail's pace of 4 years per millimeter, a slowness of 4 years per millimeter. The reciprocal of that is 1/4 millimeter per year. What about the components of this covector, which we typically write as in row form as opposed to column form for a true vector? So the components of P are, well, the vertical component is the important one here, -2. Vertically downwards, a slowness of 2 years per millimeter, or 1/2 millimeter per year if we take its reciprocal and turn it into a speed. So just by taking the reciprocal components of the covector, we get the vertical and horizontal erosion rates. But the important thing in terms of the differential geometry, the classical mechanics part of this, is that the covector takes in a vector and spits out a scalar. And it's the key coordinate in a Hamiltonian slowness space. You might be more familiar with thinking of P as a momentum, but here, because we're kind of dealing with a kind of like a geometric optics type problem, it's better to think of it as a slowness. So I said that my ambition anyway is to treat the surface as a true 2D surface in 3D. But for this initial foray, we have to keep things simple. And let's focus on a vertical slice through a simple, small catchment with a geometry like this, where we have an X coordinate starting at the mouth of the river, pointing upstream, and a vertical Z coordinate, and no Y coordinate because we're only in the plane. And we're going to have positions R will be positions along one of these arrival time surfaces of the landscape. So to make any progress here, we need a model for how erosion rate normal to the surface can be written in terms of things we're going to know. So the standard approach and essentially the constitutive relationship that underpins the models I showed you earlier is what's called the stream power incision model, which is a highly parameterized expression of how water is, during a storm, is focused and flows into channels and obviously accrues momentum. You have a velocity profile across the channel that leads to sediment transport at a certain speed and flow speed, which leads to an erosion rate across the channel, which is averaged into a single rate of motion normal to the surface, typically vertically, the vertical erosion rate, as a function, as a product separable function of flow and gradient. It typically is a power function as well, but the gradient taken some power, and which I've written with exponent eta. This seems very crude, but it's actually worked rather well to encapsulate how erosion is a function of tilt and flow. Tailoring this stream power incision model to dealing with a full true 3D surface as opposed to vertical 2+1D height field, we write that psi perpendicular, the normal surface normal erosion speed, is this function of flow, which is parameterized by distance downstream, or upstream rather, and the surface tilt. So beta is the angle from horizontal of the surface, or we can think of that as the angle of the surface normal to vertical. Now, you'll see why I went into some laborious detail for the components of the slowness covector, because we can rewrite this erosion equation in terms of slowness covector components. The gradient tan beta is just the ratio of the horizontal and vertical components of the slowness covector here. And the reciprocal of the normal slowness, so the reciprocal of the erosion rate, the erosion speed, is the normal slowness, the modulus of the normal slowness covector here. So plugging these in to the stream power incision model, we have an expression written just in terms of slowness covector components and position components. Okay? So we now deploy a technique called the Akubo Technique, or Akubo trick, which has been developed in the field of geometry, where we scale simultaneously both components of the covector using a parameter which I designate f star here for reasons that will become obvious soon. And we require that this substitution doesn't change the function. So this ultimately requires us to make f star 1. We want the functional form for f star by plugging it in. We plug it into the erosion equation. We get this, which simplifies to this. And rearranging, we get what's called the fundamental function of the manifold on which this erosion equation, this equation acts. Strictly speaking, because we're describing this fundamental function is parameterized in terms of position and slowness covector, it exists in the dual space, the cotangent bundle. So we should really call this a cometric function. Typically, this is done in velocity phase space on the tangent bundle, but we still end up with a Hamiltonian. And in fact, f star, this is the reason why I put the star, by the way, to designate that it's on the cotangent space bundle. So f star is basically a Hamiltonian, but it suffers from being order 1 Euler homogeneous in the covector. So if we scale p tilde by lambda as a positive parameter lambda that scales f star by lambda. The problem with this is that it makes f star, the Hessian of f star, singular, which ultimately means that we can't map in from the cotangent to the tangent spaces between the two. We can't map between the two. We can't deploy the Legendre transform. So the typical approach is to generate a quadratic version of this with a factor of a half just for convenience. So we define our Hamiltonian to be the quadratic of f star, which takes this form. Now, given that there's no time in this erosion equation, we're not allowing the catchment to grow in size, for example, change shape. This makes this equation constant with time and makes the Hamiltonian static. And because f star is 1, the indicatrix of this problem is a fixed shape, fixed size. The h is a half. So our Hamiltonian is static. It's order 2 homogeneous in the covector because we squared it pretty obviously. If we plug in lambda now by scaling the covector, we get lambda squared on the outside. That's order 2 homogeneous in the covector, slowness covector, which makes it Hessian regular, which means we can map back and forth between Hamiltonian and Lagrangian, which we want to do. And it also means, well, this fundamental function in its quadratic form mean we're dealing with Finsler geometry. We have a metric which is not just a function of position, but also slowness, or in Lagrangian space, a metric that is a function not just of position, but also velocity, which makes this problem grossly, generically, crudely a Finsler type problem with some caveats. Okay, so we have a geomorphic Hamiltonian, which I think, I'm not a physicist, but I think having a Hamiltonian of a problem is like, yay, okay, that's great. We have some handle on the problem now. What can we do with it? Well, we can solve for evolution of the landscape by ray tracing, by integrating Hamilton's equations. Hamilton's equations, as I'm sure you know, come from differentiating the Hamiltonian with respect to its coordinates in slowness phase space by the covector slowness covector p, which gives the rate of change of position, and a negated partial derivative with respect to position gives the rate of change of slowness. So in this case, we end up with 4 simultaneous coupled first order ordinary differential equations. But because of the nature of the flow model, which we're going to assume a very simple flow model, which captures the increase in flow downstream because it's collecting more and more water, standard parameterization, we write that the flow component is just this power function measure of distance downstream. Plug that in, we've got no vertical dependence, so this translates through Noether symmetry into saying that the vertical rate or the vertical component of the slowness covector doesn't change with time. It's set at the beginning and it's carried through along the ray. So we end up with only 3 ODEs to solve. And we can use dead simple numerical methods to integrate these rays. So here's an illustration. Again, to recap, we're looking at a vertical slice through the landscape along the topographic profile, along the channel profile. The vertical and horizontal axes are distance, and they're the same units, so there's equal aspect ratio. And the rates are very high here to exaggerate the angles of the rays generated to make them easier to visualize. They wouldn't normally be this steep, but they would be the same shape, same trend. So our erosion speed model, normal to the surface, is this separable function of flow and gradient to some exponent eta. If this gradient dependence is superlinear, if eta is greater than 1, we get a strange result. At least it's surprised me that the erosion rays, we start at a point at the boundary, remember here? And this is a point on the surface that has associated with it a tilt, which is expressed by the covector. But this erosion ray is a point on the surface which as it erodes into the landscape moves upstream, obviously, but up slightly. Not much if it was a more realistic rate, but it points into the landscape and up. Whereas if the gradient dependence is sublinear, the erosion rate points into the landscape but slightly down, which is perhaps more intuitive. Frustratingly, field data geomorphological study cannot yet tell us whether eta is greater than 1 or less than 1. But perhaps by analyzing properties like this, we will be able to look again at landscapes and decide which of these value, whether it's superlinear or sublinear. We're talking about rays, and rays that are the solution, the integration of Hamilton's equations. So this tie-in with geometric optics comes in, and without going into details, we can say with some confidence that the erosion rays obey Fermat's principle. And not related exactly, but the fundamental thing to remember about these rays is they propagate information about the boundary conditions upstream. So remember I said I always had this question, like how fast does a boundary condition take how long does it take for a boundary condition change to propagate into the landscape, even though erosion is proceeding basically vertically. So by following these rays and figuring out how long they take, we can address that question. By the same token, front motion, think of it as a wave front, obeys Huygens' principle. So if what we're visualizing here is points in black along an erosion profile, erosion surface, which, say for here, this point moves along a ray in this direction. If we imagine the locus of how that erosion might proceed, it would form a little erosional wavelet that's shaped in red here, plotted in red here. And if we take the envelope of all these little wavelets, and as they coalesce, their envelope at the next small delta time, then then we start with a profile of this shape. It moves onto the wavefront, moves in its normal direction, the blue direction, it's the direction of the covector, moves in this fashion. And the shape of the next erosion surface is given by the coalescence of those tiny erosional wavelets, which is essentially a crude expression of Huygens' principle. So right here, you can see the direction of erosion is the direction of the ray, but it's also the direction of the normal surface covector. Two directions are inherent in the erosion equation. To turn this into something a bit more concrete, remember that simplistic domain geometry I visualized earlier? Well, we're going to reflect that so that we're looking at a whole mountain landscape with, this is what it's showing in here is a mountain ridge with a river flowing this way to the left and symmetrically a river flowing off to the right. And we'll just solve for behavior in the left domain and reflect it off to the right. And we can solve for the steady state geometry. I hesitate to use that term, but the time invariant, the land surface, the topographic profile will achieve a time invariant shape if we apply a velocity boundary condition at the edge here, generate rays which propagate into the interior and are then annihilated by rays generated from the opposite side. So we only need to solve for one ray. So just going back a second to here, we generate one of these ray solutions, and all we need to do is say, look, take this ray here, we repeat that ray, we initiate it at a little time later here and place the same shaped ray here. Then we do it again a little time later, and the time difference between each ray initiation gives the vertical distance. So we know the erosion rate at that point. We initiate a second ray, a third ray, a fourth ray, etc., delta t later, which means that it's dropped by a certain distance given by its local erosion rate. So using one ray, we can synthesize the effect of erosion from a boundary. And by asking where are we along each ray at a given time, remember that big T, this ray started first, so it's reached all the way to the divide. This ray's just reached to here. This ray's only reached to here. We generate the surface. So by taking that ensemble of erosion rays, we can construct the wavefront, if you like. That wavefront is a erosion profile of constant shape. But the important thing to remember is the erosion profile is not the erosion ray, right? That you use it to construct it. And right in the middle here, the drainage divide is where rays collide with each other and annihilate each other in a cusp. So to visualize that one more time, this is just that one half, the left half. And the top picture here is showing if the dependence on gradient is superlinear, if eta is greater than 1, then we get rays that move into the landscape but point up slightly. Whereas if gradient dependence is sublinear, the rays move into the interior but tend downwards. But the shape of the land surface, the shape of the topographic profile is pretty similar. So if that's all you have, it's hard to tell which is going on. Okay, so I said that we constructed a quadratic Hamiltonian, which allows, because its Hessian is regular, we can perform a Legendre transform and go from the Hamiltonian to the Lagrangian, which I could have written out in full here, in full algebraic form here, but it's pretty ugly, so I didn't. And this Lagrangian is also static, also takes a value of a half, because P dot V is 1, H is a half, so L is a half. Excuse me while I take a drink. And classical mechanics says that we can take this Legendre, so we can take the Laplacian and using a variational approach, ask what are the trajectories of motion, which we've also already solved using Hamilton's equations, but we could alternatively solve for evolution of the surface in using the Lagrangian. And if we examine we say, for example, ask how long does it take to get from point A to point B along a trajectory, an arbitrary trajectory, what is the trajectory that's actually taken? And it's the one along which the travel time is stationary. And it turns out it's minimized. So essentially, what the Lagrangian tells you is that the trajectory that the erosion process takes from point A to point B is the path of least time, the path of shortest erosion time. So this is another key result from this work, which is that we can assert that landscapes are the consequence of a variational principle, which is that of points on the surface taking the path of shortest time. That variational principle has not been articulated before. May not be right, but it hasn't been articulated before. I said that because we're dealing with a parametric, well, we're dealing with a parametric Hamiltonian and Lagrangian whose fundamental function is Euler-1 homogeneous, we're dealing with Finsler geometry. One other way to look at this is to write the metric tensors of the problem, which we get by doubly differentiating either the Hamiltonian, or which gives the metric tensor on the slowness phase space, or we can correspondingly differentiate the Lagrangian, a half f squared, doubly with respect to velocity, and we would get the metric tensor on the velocity phase space. And those tensors are mutually inverse. And looking at this tensor, again, we could write out these tensors in full here in algebraic form. It's doable, and look at their properties. And we find that actually positive definiteness, etc., are not always obeyed depending on eta and depending on where we are. So it's perhaps more strictly correct to say we are dealing with a pseudo-Finsler manifold and a conic pseudo-Finsler manifold. Conic in the sense that a portion of that phase space, not all of it. But it's not clear to me what results in Finsler geometry this limitation makes unavailable. What can I still use? What can I not use? That's not obvious to me. But it's important that we know exactly what we're dealing with. So apparently we're exactly dealing with a conic pseudo-Finsler geometry. And specifically, although this is in terms of the metric tensor on the co-metric tensor on the slowness phase space in Hamiltonian side of things, we can write that in terms of what's called an alpha beta generalized Kropiner metric. This is the mathematician Kropiner who classified this particular type. So this is just to say that we, I think, can identify the type of Finsler geometry we're dealing with. Typically, a Kropiner metric applies to the Laplacian side of things, the tangent bundle side of things, but I've seen it used in this form for the Hamiltonian side of things too. It just says that the fundamental function takes a particular form, where there's a Riemannian part here and a non-Riemannian part here. So that, in a sense, simplifies what we need to deal with in Finsler terms and makes available, it makes it easier to access which part of the literature is relevant to this problem. And eta comes into play here, that scaling of gradient. So we can do another thing because we're dealing with this kind of geometry. With a typical approach of the Lagrangian is you solve the Euler-Lagrange equations, you manipulate the Lagrangian into Euler-Lagrange equations, which gives you the dynamics. For this kind of problem, the dynamics are expressed as a second order differential equation, which includes the geodesic coefficients. So this, in other words, we're saying that because the trajectories of motion, the erosion rays, are paths of least time, they are geodesics. And the geodesic coefficients, so remember, just to be clear, R is position. So R double dot is the acceleration of a point that's a function of position and velocity in this form. And that second order differential equation, a set of second order differential equations, there'll be two of them in this case, have geodesic coefficients, which have this rather intimidating form, intimidating for me anyway, which is I am skating over the fact that I've been using occasionally tensor coefficients that are with Einstein notation, Einstein convention of contraction over like coefficients, etc. So the geodesic coefficients are a function of the metric tensors and velocity. And again, I could write out in algebraic form for this problem the geodesic coefficients. And they take, as far as I can tell, relatively simple form. And in general, this also brings into play the idea of a geodesic spray, which is that the vector field I should say the Hamiltonian vector field gives a vector field that we call the geodesic spray, whose integral curves when projected into real space are the erosion rays. So in any case, there is a connection, and there are aspects of the study of this kind of problem in geometry that may, if I look closer at the and I apply more carefully and apply in more detail things like aspects, properties of a geodesic spray, I might be able to find fundamental properties of the geometry of the erosion equation and fundamental properties of how landscapes evolve. That's the hope, okay? By knowing these aspects of the geometry. So this is the last substantial slide of the talk. This is just to emphasize again this, for me, rather surprising result that we can express the anisotropy inherent in the erosion equation in terms of two directions, one being the slowness covector. So the herringbone-like symbols here indicate the direction, and the magnitude is the density of these crossings of the herringbones, expresses the magnitude of the slowness covector. So the direction and magnitude of the slowness covector, which is surface normal. This is this is a time invariant topographic profile. And then the erosion ray vectors and their length and direction are given by the arrows. So down at the mouth of the river, the slowness covector and the erosion rate velocity vector are almost orthogonal. But as you proceed into the interior, that anisotropy reduces. And in fact, for eta is less than 1, right up in the interior, when you get towards the hill slopes, the disparity between the covector direction and the velocity vector direction is almost gone, and you're almost in an isotropic situation. And again, the erosion rate vectors point up if the exponent is greater than 1, and they point down slightly if the exponent is less than 1. So we have a quantification of erosional anisotropy. So to conclude, we started with the observation that, the hypothesis really, that landscape evolution is essentially experiences a geometric straitjacket, in the sense that the rate of change of landscape geometry is determined by its geometry. And I've shown how we can express that as a geomorphic Hamiltonian by using trickery and parameterizations available in differential geometry. And that this erosion process takes place in a Finsler geometry of a kind. We've identified a variational principle which says that this land surface, this landscape geometry evolves according to a principle of least erosion time. And it shows that erosion acts in two directions at the same time. One, normal to the surface, which we express using a slowness covector, and another very oblique, almost 90 degrees in some cases, to the surface with a ray velocity vector. And it's that ray velocity vector along the erosion ray which takes information about boundary condition changes and propagates them into the landscape. And the time it takes for that information to penetrate the landscape is the time it takes to traverse an erosion ray, a trajectory along an erosion ray. So where am I going with this next? The obvious thing to do, we set up a very simplified kind of geometry and landscape evolution sort of context, where we just had a single simple catchment with a vertical boundary condition, which is a velocity slip condition, allowing the landscape to uniformly rise, relatively speaking. But what if we allow the erosion rate at the boundary, the slip rate, sorry, to vary? That will generate rays. In this visualization here, we've got rays being initiated initially here, and as the slip continues, the successive rays are generated. But at this point here, the slip rate increases suddenly, so the arrays, again, taking that boundary condition information, carrying it into the interior, they move faster because the erosion rate is now faster at the edge because the slip rate is faster. So these rays move quicker and they catch up with the older rays and they intersect with them. If this was an optics problem, this would be caustics. Here they form cusps. So this is the same information but expressed in terms of those arrival time surfaces This is the first arrival, second, third, fourth, etc. And because the erosion rate is slow, these arrival time contours are densely packed. Okay, so this is a line here is the topographic profile at a given time. And then when the erosion rate at the boundary increases because the slip rate increases, the erosion rates go faster. So the overall landscape must be evolving faster and it has to be steeper. And as a result, you can see that what you effectively got here is a little waterfall propagating into the landscape. And at what we call this a nick point. And one next step for this project will be to try to figure out how fast these nick points form, how do they form, etc. And perhaps we could then make observations in the field to confirm whether the theory is correct. Ultimately, what I'd really like to do is to construct a fully 3D version of this with a surface being solved as a true two-dimensional surface in a 3D volume. But this won't be very easy because we won't be able to make such a simplistic parameterization of the flow behavior, that flow component. We'll probably have to resolve channels in some fashion, which will be technically difficult. And ray tracing, if we stick with that, is a lot more difficult in 3D. For example, when rays cross over each other, they don't cross over in a simple interaction that's easy to track. And obviously in 2D, rays cross, they intersect. But rays crossing in 3D, they don't intersect. So if you're going to figure out how a erosion front moves and construct it from rays and figure out where these nick points and cusps form, is going to be technically more difficult. This picture here is showing streamlines, and streamlines are not geodesics, but it may be that geodesics of a full 3D problem are, when projected onto a flat surface here, maybe those geodesics, the erosion rate geodesics, follow the same lines as streamlines, in which case we could just deduce that drainage divides are the cut loci of this problem, and ridges between basins will be conjugate loci of the problem. So there's some wealth of literature on how to treat geodesics and cut loci, etc. Perhaps we can leverage those to understand how the complexity of a 3D landscape actually evolves. That's the hope. So anyway, thank you very much for your attention, particularly during these difficult times. I think I'll stop there. Thank you.
Thank you very much, Colin. Thank you very much, Colin. So again, thank you very much.
Could you hear any of that?
Sorry?
Could you hear any of that well?
Yes, I hear very well. Just that I was using a speaker to, and now I'm talking in my smartphone. So that's some echo. Well, I must say that our students usually are very shy. I hope they are not shy today. So any of you want to ask any questions? So don't be shy, people. I know Pedro is someone who really likes classical mechanics, so probably want to ask something. Paulo is expert.
Please ask a question. Hey.
Hello.
Are you listening to me?
Yes, yes, I can hear you much better than Petrus, actually.
Hi. I'm a geologist. I work at the Brazilian Geological Survey, and more often than not, we track sediments for works in agriculture or even for construction materials. And more often than not, even from natural processes, We do not see the the prevalence of this dynamical equilibrium in erosion. There are
Hmm.
several patterns of erosion and transportation of sediments that look counterintuitive. They are really not uh, pretty in the sense of the preservation of the original geometry. Sometimes blocks fall. Sometimes, you know, the works of the water and the wind and the gradient of temperature from day to evening give the surface a very brittle, a very fragile matrix or fabric, rather to
Hmm.
say. And
Okay.
sometimes there are huge blocks that go downhill. They just drive down because their interface with the actual ground break down over their under the pressure and weight. So I would like to know if this model of yours, it's beautiful. You know, it's beautiful. I saw some things that
Thank
I
you.
could totally relate. I could really see some things that some conclusions that you guys arrived that were just beautiful, simple and beautiful. But to tropical lands, to tropical landscapes, and to surfaces that are really not that ideal or that really do not follow the dynamical equilibrium of erosion. Do you know if there is a huge amount of corrections to be applied or something like that?
Yeah. Okay. That's an excellent question. If we just focus on, you can still see the screen, right? Um,
Yes, I can still see the screen.
so before I get to that, let me just say, first of all, absolutely, this is why I raised at the beginning the point that real geomorphology is a pretty dirty business. It's very complex. It's, I should have emphasized, at short time scales and spatial scales, it's particularly complex. Um, and issues like you say, rock falls and debris flows and landslides and temporary sediment storage and individual blocks and individual bar forms and rivers, all sorts of complexities that make this approach look wildly simplistic. Those are all true. But it's also why I emphasized why we're thinking on a, think of this time scale of tens of thousands to millions of years. A lot of those instantaneous complexities or short spatial scale complexities vanish in the long-term averaging crudely. Um, so that doesn't really help you sort of look at a landscape and say what's happening now, except to say, well, on the long term and the larger scale, rather than just a few meters, um, broadly speaking, this kind of geomorphic Hamiltonian applies. Um, I'd also say that if you want it's like a take-home thing, a take-home message, I think for me, harking back to when I look at landscapes, say somewhere in Japan, where I see there's evidence, for example, in landscapes here of an erosion wave that's propagated into the landscape as a result of some sea level, base level fall or whatever, or relative uplift of an entire peninsula. And you see this evidence of this wave in the landscape as a subtle change in the gradient of the landscape with a wave-like pattern indenting. That that arises because of this double difference, this two directions of erosion. I think it's, and so it works on that scale, right? Those features are explainable now with this kind of model. So in other words, I think it's okay to look at this very simplistic model, this very idealized model, and apply it when you look at a river and you go, okay, what direction is this eroding? There is, it erodes vertically, not vertically. So it erodes normal to the surface, subvertically downwards, but it's also acting upstream at the same time in a way that is encapsulated in the erosion equation and with this anisotropic behavior. And that if you wanted to, you could go to all the trouble of doing all this this classical mechanics treatment to your specific river and understand what direction and how fast is the nick point propagating upstream. It gives you that sort of mental toolbox, I guess, to understand what's going on. But yeah, because it's such an idealized model, it can't be really applied to a particular, it's hard at this stage anyway to apply it in particular. But the reason I brought up this picture is I was saying, okay, so one of the key, there are so many simplifications in the model, and one of them in the numerical examples I showed you was that we make the rate of uplift or the rate of vertical slip constant. And in places where you do your field work, that doesn't apply. You could zoom into a very small scale and make that approximation work much better. But yeah, dynamic equilibrium steady state, I don't like it very much either. It's just in this case, it's a way of constructing the most simple numerical solution to see what happens. And as soon as you introduce complexity, you'll start to see interactions like this with rays crossing over, waterfalls, nick points forming, complexities that are still expressible with this model, but they haven't been included in the numerical simulations so far. So I can't present them to you beyond this sort of simple demo here.
Follow-up question.
I always feel that there's some stochastic components that are missing. Then when you integrate over time, that they will cancel out, right?
Sorry, yeah, there was another question coming in, but yes. Yes, there is a very important role of stochasticity, which is why I waved my arms and said, well, on the long time scale, you just average these things out. But the averaging process might actually introduce specific behavior, which mucks everything up, but introduces slightly different new behavior. For example, these nick points might form. If you just have a simple fluctuation in the flow, it might be enough to make rays wobble in their directions and intersect even under long-term quasi-steady conditions. So you'd have nick points forming even though on the long-term averaged, they shouldn't. So I don't know if it's necessary to introduce stochasticity so much as variability of some kind, perturbations on a small scale, periodic perturbations, those sort of things, but introduce stochasticity, and yeah, absolutely, especially in 3D. In this 2D slice, it's less important, but in 3D, it's going to be extremely important in determining the overall network. But there was another question, sorry.
Yes, I need 5 minutes because my pizza arrived, so I'll ask the question in about 5 minutes, okay?
Good for you, good for you.
Okay, so you say that the stochasticity can introduce some pathologies, but well, see, I always expect some. I asked you it before, but I expect some kind of roughness in the landscape, and
right.
Well, stochasticity can introduce that. And
sure.
You have a tutoring mechanism, and you have a transport process introducing your dynamics, but well, the roughness probably came from the stochastic component, some sort of Legevin dynamics.
Some sort of
Legevin dynamics, something like a Brownian motion. That, well, I don't know where we will introduce it.
Well, my first real paper was, as you know, treated river channel formation using percolation theory, which is assumes a quenched noise in the landscape, in the substrate across which a cluster, whatever, grows. So I'm definitely on board with your suggestion that there is noise in the system and it will manifest in some way that might be KPZ or Brownian motion, or for example, there's been interest in the the Lerner equation, the Schramm-Lerner, I think it's Lerner equation. I'm rather new to this particular mathematics, which is a stochastic version of the Lerner equation. And it's been used to explain why you have drainage divides that are irregular in geometry. So that roughness in a drainage divide, which is I suppose a snapshot of the roughness of the overall landscape. There are arguments that it arises because of an essential Brownian motion. The Schramm-Lerner equations essentially have Brownian motion built into them, right? Yeah, what I would say, for example, drainage divides, I said that they might be cut loci of this problem, where geodesics that are erosion rays, where the erosion rays propagate from two different directions, from one catchment exit to another catchment, propagating into the catchment and then colliding at the drainage divide. The geometry of that drainage divide could be a cut locus. And there's work in the field of geometry, Finsler geometry, which says that you can predict the fractal dimension of a cut locus under very, very limited conditions. In their case, the papers, the work done on this is on the S3 sphere, for example. It's not exactly pertinent, but there are results in geometry which say that the geometry of the cusps that were formed by collisions, by interactions of geodesics, have a predictable geometry, whether it be triangulable or non-triangulable or even fractal, and those dimensions might be predictable. So that might be a way, if one could develop a model for the dimension, the roughness of a drainage divide, for example, and then look at the values of the properties of natural drainage divides, compare the two to at least attempt to validate the model.
Yeah, follow-up question. In Brazil, there is a quadrilateral ferrífero region in the southeast of Brazil. It's a very old ground. It's a very old rocks. And the deposits, the gold, diamond, and platinum deposits are all sedimentary, transported, placer deposit.
Mm-hmm.
So not the host rock, the original rocks are about 2 billion years old.
Mm-hmm.
So the time factor, you could do exactly what you did. You could just throw it out the window, you know, the small events, the breeze flows, the earthquakes, rocks falling, and etc. You could just throw it away and assume that everything went according to the model, because 2 billion years have passed. Supercycle continents, you could just, you know, and there is a cratonic region, not a single mountain range here from the last 2 billion years.
Yeah,
has arisen. So how would you feel about applying that model to some kind of mineral deposits prospection?
Well, I think if there's an application of this model at all, let's go backwards a bunch. Go back to the beginning. Where, for example, this kind of model is now available, very realistic looking thing. I always hesitate. The kind of work I've always done in geomorphology has been so abstract and idealized and theoretical that when confronted with the how do you use it in the real world question, It's like, I'm not, I'm not entirely sure.
You really were not expecting that question,
huh? I'm always expecting that question, and I never know how to answer it very well, other than saying, well, I'm a theoretician, don't bother me with the real world, you know. But what I would say, first of all, that if you really wanted to simulate, say, the direction of motion of sediment and how much and how far and what patterns you might see, there are beautiful numerical models, some of them available. You can just download them and run them based on Python, etc., and you can run them yourself. They all, like this model here, basically apply the same stream power incision model, and they all solve them in this 2+1D fashion. So that would be one, if you wanted to do a numerical modeling and see where your sediment went, where your places were formed, you could probably use a model like that, perhaps. I'm not sure they're ideal for it. The work that I've done might say, well, okay, you could reformulate this model, like I say, in a 3D fashion. You don't need to develop a whole Hamiltonian apparatus to set up an erosion and sediment transport problem in full 3D using implicit functions, using level sets. You could do that. It would be slower. I'm not sure you would gain a lot if you're looking at a very large scale where the approximation that erosion is basically vertical downwards works. If you're in low gradient systems, it won't make that much of a difference, except that, as I emphasized, nick points and the horizontal motion can't be modeled. Even though they're a fundamental aspect of how this landscape evolves, they can't really be modeled without fudging things. But you know, again, practically speaking, if you're chasing where placer deposits form, you probably don't need to worry or want to worry about that. But what this work my work has shown is that you could write a model like this using a level set approach, and you would get different behavior. Perhaps the drainage divides would be more dynamic. Perhaps nick points would arise and be modeled more faithfully. But you need to construct a 3D level set version of the problem. And like I said, there would be technical problems associated with that, and conceptual ones like how do you then model flow field where you start to have to resolve actual channels. You can't just parameterize them out. But so I think in reality, the most useful thing to take away from a talk like this, if you are dealing with practical real world problems of erosion, is just it gives you a way of understanding that erosion is not just downwards. Okay, it's not just a vertical process. It's normal to the surface, but it's also into the landscape at a very strong angle. And if you want to understand like where your nick points go and how you know how the basic dynamics work, it's these two directions of erosion at the same time. It's that conceptual take-home message, I think, is the most important thing.
Yes, thanks a lot.
Well, if anyone wants to ask another question and don't want to speak, you can write it in chat so you can read and ask it. Some people said, congratulate you for your presentation. But anyone want to ask any other questions, people?
Yeah, maybe they're all shy. They shouldn't be
Well,
shy, because, you know, especially if they're physics and mathematics students, they're all much better at this than me. I'm just muddling through the maths and physics.
Well, some of them might be a little bit intimidated by the mathematics you use. That's not a very standard thing. We already discussed it. Francioli, do you want to ask something? Anything?
Go on, you guys, you can just type it. It's
Yes.
Probably the work here is so out, what we say in English is so much out of left field for most people that even in my field, my specialization of geomorphology, it would it would be a surprising, this presentation would be an oddity, I think. They would look and go, oh wow, that's not really,
Yes.
you know, this is an unusual thing. And the mathematics would be very unfamiliar to people in my field. This is why, yeah, I expect
No, but
that.
even for a mathematician, someone with experience in differential geometry, he might not have familiarity with classical mechanics to follow up.
Oh, okay.
And the other way around, say some physicists with experience in quantum mechanics. So he will probably not know enough differential geometry to understand every detail. That's a lot of things put together, and I really like that.
Yeah. I suppose in particular, this Finsler side of things is a bit of a niche topic in differential geometry. I guess 100 years ago, there was some expectation that maybe general relativity would have to be revamped using Finsler geometry. Cartan was the guy who kind of did all the work on it, and he had his own take on general relativity. So, but it didn't turn out to be very useful. It's sometimes a pain in the ass to work with compared to Riemannian geometry.
Yes.
So it's interesting, but it's annoying sometimes, and there's a lot to learn.
Yes. Well, you said something sometime that, well, if Earth is really flat, it's very much better to do calculations, right?
Yeah. Yeah, and then there's specifically interested in geodesic sprays. I'm only really beginning to understand what they are and what they mean. But are you familiar with geodesic sprays? You seen it come across this term much?
Not.
Okay, so it's good. That's good to know. I shouldn't be expected to know what they are. But yeah, apparently it's in the field of differential equations. If you have a second order differential equation of the form that I showed, r double dot plus some function of r dot, if that function of r dot is Euler 2 homogeneous, you have a geodesic spray. There is a vector field whose integral curves are solutions of that second order differential equation. And you don't even doesn't need to have any Lagrangians, Hamiltonians. This is all separate from that. It's a property of a generic class of second order differential equations, apparently. But I'm skating on thin ice talking about general properties of differential equations. If there are any mathematicians still listening, I don't want to go any further with that thought, but it's possibly interesting.
Nice. So I believe we will not have any other questions. Just let me tell you that during your talk, I was testing Google Meet language translator and language capture, and I know you like that kind of stuff. And it really works pretty well when we talk. When I talk, they mess up everything.
Even with the specialist vocabulary?
Oh, there's some minor mistakes there. But it's really good that they say things like .r and everything.
Ah, yeah. When you describe equations, it's like, what on earth is that?
It's really, really nice. That's the first time I use it. So let's thank Colin once more. And
thank you.
Well, it's really nice to finally talk to you face to face.
Yes, it's been a long time to get to this point. Finally, we get to meet properly.
Finally.
Thank you for the opportunity.
Let's do it again time.
And good luck with current situation. I hope things work out.
Well, elections are in the next year. We hope that we'll solve something.
Yeah. Yeah, we have elections here soon, but they're not going to solve anything. It'll be the same old, same old.
So, so Erickson, I don't know, you're not from Wafcat, right?
Not from where?
Not from
Erickson,
where? Eccleston. Name is Eccleston.
Eccleston,
It's a very
Eccleston.
different name anywhere in the world.
Well,
Sounds Italian.
I'm from Brazil. I'm Brazilian. I graduated in geology in 2012, and I got here by accident because a friend of mine suggested the subject because we were talking about the development of soil in different types of grounds and rocks and environments and ages of the earth. So he thought that this subject would interest me. And indeed, it did interest me.
Well, thank you.
Very
Thank you.
good. I'm telling you, it's a very good model. It's elegant. It's simple, despite
very elegant.
the mathematics. Not my not my plate. You know, not my favorite topic. But the idea and the concepts are, I would say, brilliant and elegant, which is really rare in geomorphology because, as Colin said, geomorphology is a dirt business. It's very very intricate.
It's a dirty
Correct.
business. Yeah. Yeah.
I've placed my email in the chat. It's very simple. It's eccleston@gmail.com.
Okay.
So it's easy. Anyone interested in contact me, I work for the Geological Survey of Brazil. So everything I work on has to be public and has to be for free.
Ah,
If you are interested in any kind of collaboration, if you feel that I can help with anything, feel free to contact me.
well, thank you. And thank you for your kind comments. And again, Petrus, thank you so much for this opportunity. I noticed in recording the presentation, it came to 59 minutes and 16 seconds or something like that. So how's that for getting things on exactly 1 hour?
That I really don't know, but we have other presentations that are actually longer. Actually,
I tried to get to
it's our
1 hour, so you know
YouTuber.
yeah. All right.
So thank you, everyone. I hope everything stay healthy, take care of yourselves, and I hope you will talk to Colin soon.
Yeah.
And the invitation is open. When everything passes, come to visit us.
I really hope I can do that one day. Yes, when things have calmed down, that would be really good. All right. Well, thanks everybody.
Goodbye, everyone.
Bye.
Bye bye.